Yeah. Okay, well, let's get started. Yeah, so hello and welcome everyone to the 11th lecture of our CUDA programming. So, so in the previous lecture, we saw that synchronization construct, which is called a sync thread, which synchronizes the threads, which is used for synchronizing the threads within, uh, the same thread block. And then we saw multiple examples related to that sync thread synchronization construct. And then we saw that API called as CUDA device set cache config, which is used to set the amount of uh, which is used to specify the amount of shared memory and L1 cache we want. So we saw typically that we can specify 32 KB of shared memory and 32 KB of L1 cache, or we can specify 48 KB of shared memory and 16 KB of L1 cache, and vice versa. So we saw that we can set or specify these things using that API called as CUDA device set cache config. And then we saw the and then we saw that dynamic shared memory thing, right? That when, let us say that we want to specify the size of the shared memory based on some argument that is being provided by user at the runtime, then how can we do that? We saw that we can do that using something called as dynamic shared memory. And then later, towards the end of that previous lecture, we briefly touched upon the bank conflict. We saw what is bank conflict, and there we stopped in the previous lecture. So that was the brief recap of the previous lecture. Okay, so for the today's lecture, we are planning to cover the bank conflicts in detail. We'll be covering bank conflicts with some examples related to it. We'll also see how the bank conflicts occur and all those things. Then we'll see briefly touch upon the texture and constant memory. We'll see one program related to both texture and constant memory. And towards the end, we'll see different things related to the CUDA compute capability. So what is CUDA compute capability and how it is related to the family of GPUs and all those things we'll be seeing towards the end of this today's lecture. And with the end of the today's lecture, we'll be concluding the memory aspect of the GPU. And yeah, so that's our agenda for today. We'll be completing the memory aspects. And yeah, so I think with this we should uh, get started. So yeah, so this was where we left off, right? Like um, we saw I mean we saw that there is something called as bank conflict, which is very similar to something called as which is very similar to memory coalescing that we saw. But we saw that this bank conflict is something related to the shared memory, while the while this memory coalescing is related to the DRAM of the GPU or the global memory. And and then we saw that the shared memory is composed of something called as bank. And and typically shared memory is organized into the set of 32 banks. And yeah, so we saw that in the previous lecture. And then we also saw that if two warp threads try to access the same bank, then their requests are served sequentially. So accesses to the same bank are sequential, that we saw. So two warp threads accessing the same bank, then the request will be served one after the another. We saw that with that typical analogy that people are going to grocery shop for buying something, and let us assume that there is only one shopkeeper in that shop. Then in that case, the request of multiple people will be served one after the another. So in that case, bank was that shop or shopkeeper, and the people were the requests that are made by the memory requests that are made by the warp threads. So we saw that thing. And yeah, that is where we left off in the previous lecture. So yeah, any questions up till that point? Yeah, I think that part is clear. So anyways, let's get started with the today's content. Okay, so before starting further, so let us say that I want to clarify one point here. Okay, so let us say that your program is having both issues. This memory coalescing, that is, you are having uncoalesced memory access in your program, as well as there are bank conflicts occurring in your program, which is your CUDA program that you have written. Then in that case, what is important, memory coalescing or the bank conflicts? Can anyone quickly tell me which one? I mean, which one should we give more priority for the optimization? Quickly, based on the things that we have covered so far, like you might be able to answer it from this thing only, this point only. Which one should be given higher priority, memory coalescing or bank conflicts? Which thing you should optimize first, and then go with the which should have the higher priority among both. Quickly, let me go. So, the chat. I hope that question was clear. Okay, anyways, I'll answer this question and leave next question for you people. So, okay, so let us say that our program is having both the things, uncoalesced memory access as well as the bank conflicts. Then first we should go for uh, optimizing on the, I mean, making the memory accesses coalesced. Why? Because if you people remember, the memory coalescing is something related to the DRAM or the global memory, and accessing that global memory is a very costly operation. If you remember from the first lecture of that memory, that accessing the global memory takes around 400 to 800 cycles, and if the memory accesses are uncoalesced there, then lot of memory requests or the access to the global memory will be made, and that will eat up lot of time. So first thing is improving memory coalescing, and if that is done, if your accesses are completely coalesced, then if your program is having bank conflicts, then you should optimize for the bank conflicts. I mean, removing those bank conflicts, optimizing your program by removing those bank conflicts. So yeah, so again, bank conflict will only occur when you are using shared memory, and let us say you have a very nicely parallel operation, and you are using shared memory for performing that operation, and during that parallel operations that you are performing, there are a lot of requests by the work threads which are causing this sequential bank accesses. So that will cause bank conflicts, and we'll see how, I mean, we'll see the examples for them in the this slide or the next slide. So yeah, so I hope that is clear up till this point. Uh, okay, any questions? Okay, Thomas is saying bank conflicts, memory coalescing. So Vasanta is saying bank conflict should be given higher priority since shared memory is quickly accessible. If it is accessible, result drastic in performance. Yeah, that is correct. That it can be accessed very quickly, but if you see, if your memory accesses are, I mean, uncoalesced, then that is the biggest bottleneck that I would say, because that will take even more time. So I hope that is clear, that what I explained. Um, okay, anyways, if there are any questions related to this point, then you can unmute yourself and ask. But meanwhile, I'll move further so that, yeah. So, okay, so let us move on and understand this point, that consecutive words are stored in the adjacent bank. So let us understand this point with the example that consecutive words are, so okay, so consecutive words in shared memory, first of all, consecutive words in shared memory are stored in adjacent banks. So let us understand with this with an example. So let us say that you have this type of shared, oh my god, okay, I'll just do this, int shared int ARR 1024. Okay, so we have some shared, we have some array which is declared as shared, so it is inside the scratchpad memory or shared memory. And what point that we, I mean, what point that this line is saying that consecutive words are stored in the adjacent bank. So okay, so here the consecutive words are like this, right? So ARR of 0, and they are stored in the consecutive bank, so it will go in the bank 1 or bank 0, let me say. and ARR of 1 will go in bank 1, ARR of 2 will go to bank 2, and so on. In the same way, ARR of 31 will go to the bank number 31, and this pattern will repeat in wraparound fashion. So ARR of 32 will go into bank 0, ARR of 33 will go into bank 1, ARR of 34 will go into bank 2, and so on. This pattern will repeat for all other elements or all other words inside this array. Since this is an integer array, one integer is one word, right? So yeah. So let us come back to the slide. So that is what this point is suggesting. Consecutive words are stored in the adjacent bank. So if you see this in that example that I showed in that chat, ARR of 0, ARR of 1, all those are consecutive words, and those are stored in the consecutive adjacent bank. So they were stored in bank 0, bank 1, and so on. Since we are 32 banks, so 0 to 31 words are stored in those adjacent bank from 0 to 31. And this is typically useful, like, because this is very much similar to memory coalescing, if you see. So let us come back to this thing again. So if you see this, now let's say if warp threads try to if our accesses are let's say warp threads are accessing this consecutive memory location from ARR 0 to ARR 31. So thread 0 is accessing this ARR of 0, thread 1 is accessing ARR of 1, and so on till thread 31. So these are warp threads, right? 0 to 31, and they are accessing like this. So now if the access pattern is like this for the shared memory, then what will happen? So each thread is accessing something from different bank, if you see. If each warp thread is accessing something from the different bank, and if that is the case, then this request won't be sequential. If you see, accesses to the same bank are sequential, but in this case, all the warp threads are accessing different banks. So accesses are all in parallel, and if you see, this is very much similar to memory coalescing. I mean, it's not actually very same to memory coalescing. It's not actually the memory coalescing, because in memory coalescing we have seen that when warp threads accessing same word from the block of 32 words, then memory accesses are coalesced. But here threads are accessing different banks, and hence the accesses are done in parallel, and the latency is just for the one memory access, right? So in some sense, in both coalescing and this bank conflict, if the accesses are done as per the, accesses are done in the consecutive fashion, then we'll just need one memory access, as we saw in this example for this shared memory also, right? So this entire thing will be served in just one memory request for the warp threads, because they are in the adjacent bank and the accesses are parallel for the different banks. So I hope that this is clear. Yeah, so it's very similar to memory coalescing. It is useful in very similar fashion as we saw for, the memory coalescing or the coalesced accesses. But there is one exception here. So I told that the accesses to the same bank are sequential. So warp threads accessing same bank will lead to sequential access to the memory. Sequential access to the word inside that bank. But if warp threads accesses the same word inside the same bank, then requests are not sequentialized. So let us also understand this with an example here. So let us say that let us continue with this example itself. So ARR of 0 was stored inside bank 0. Now let us say that thread 1 is accessing ARR of 0, and thread 2 is also accessing ARR of 0. In that case, both the threads, which are the warp threads, so please note that both the threads are the warp threads, and those both threads are accessing same word, which is ARR of 0, and they are also from same bank. So in that case, they are not, these accesses are not sequentialized, because that word is, it's common between both the warp threads. So those accesses will not be sequentialized. So the accesses that will be sequentialized are the accesses that are made by warp threads from the same bank, but to the different word. Again, accesses made by warp threads to the same bank to the different words are sequentialized, but accesses to the same bank of the same word are not sequentialized. They can be served in parallel, because just one word will be brought and the another thread will just will just make use of that fetch word, and yeah, it does not require to refetch it again. So that's the reason. I hope that's clear. If there are any question up till this point, then please feel free to ask. I'll probably pause for a few seconds here. Any questions? Okay, I am thinking that there are, I'm hoping that there are no questions. So with this, let's move on further. Okay, so yeah, so our next task will be to write the code corresponding to the case when there are no bank conflicts. So I request each and every one of you to try writing the code corresponding to the case when there are no bank conflicts, and please post your answers in the chat so that we can discuss the possible ways in which we can write that code. So I'll pause here for a moment for you people to try out, and yeah, then we'll move ahead after a few seconds, probably a minute. Okay, yeah, for our discussion, let us keep it simple. This concept of bank is only limited to the shared memory. But as far as my knowledge is concerned, like I've also studied this bank thing in the CPU's DRAM. So I'm assuming that there is something called as bank inside the GPU's DRAM also. But let us not worry about this right now. Yeah, so I'll just say that. Yeah, I'll just leave it there, because I think that this bank concept is quite generic. It's not very much limited to the what I can say, the shared memory, but it comes it becomes useful for the shared memory because of the way we access it. What is difference between coalesced access and warped access? Okay, so warped access is if you say coalesced access, then I think you might remember that definition, right? That when warp thread accesses the words from the same block of 32 words, then the memory accesses are said to be coalesced, because will only make uh, only one memory request will go to the memory controller of the CPU. So that is coalesced access. But the warp access is like, it can be any, right? Warp threads can access anything in any fashion, right? Because of simply execution. So warp thread will execute some instruction. Each thread in the warp will execute some instruction, and they can access some memory location, and that is something called as warp access. So yeah, so warp access is something like what all the threads in the warp, what memory location all the threads in the warp are accessing. So I'm hoping that that is clear. What is warp access and coalesced access? Okay, request each and every one of you to try out what can be the code corresponding to no band conflict. At least some small snippet that you would like to um, highlight, which would result in no band conflict, based on what we have understood so far using these 4 points. I'll wait here for a few more seconds to let you people try. Okay, there is some response. ARR of thread ID x dot text equals to thread ID x dot x. Okay, I think that's probably correct. So any other response apart from this? Would anyone else would like to try out what can be the possible answers corresponding to the no bank conflict? Okay, I think Gokul has also typed something. Since it's sequential, can't we access multiple banks at the same time given that each index in the array has its own bank? Can't we access multiple banks at the same time given that each index in the array has its own bank? Yes, that is what will happen, Gokul. I hope that is clear. Because each and every element is going into different bank, all the accesses will be parallel. So here, no two no two memory locations are, no two words of the array, at least for 0 to 31, are being stored into the same bank. So this is precisely the case where there will be no bank conflict. And I have asked few people to write the code corresponding to it. So this can be one of the way. So let us see this. Okay, let us try to understand this. So we have this GPU kernel, which is named as no bank conflict. And inside this, let us see what we are doing. We are declaring this shared, we are declaring this array S, which is of size 1024, and it is marked as shared, so it is common across all the threads of the thread block. So yeah, so and the access pattern that we do here is like this: thread ID x dot x is equals to thread ID x dot x. So let us understand what is happening. So thread 0 will access S of 0, thread 1 will access S of 1, thread 2 will access S of 2. So if you see, this access pattern is exactly same as the one we saw here, right? Here instead of ARR, the array is S, shared array S. So S of 0 is accessed, then S of 1 is accessed by thread 1, S of 2 is accessed by thread 2, and so on. S of 31 is accessed by thread 31. So if you see, all these words are going into different bank, and hence if you see, this program will result into no bank conflict. Sorry, so this program will result into no bank conflict, and I hope that you are getting it. If there are any questions here, then please ask. Why multiply by 1 in the example? Okay, that is just for it has no any such purpose of we will understand that this why we have multiplied it by 1, but it won't affect anything. This what I am trying to say here. If you see, multiplying it by 1 doesn't have any effect uh, on the no band conflict part, right? Because uh, if you multiply it by 1, this thread ID x dot x will remain the same, right? Anything multiplied by 1 will remain the same. So that part is I hope clear. So okay, that's fine. If there are no further questions at this point, could you explain again, but comparing with how we usually do? Could you explain? Sorry. Could you explain again, but comparing with how we usually do IDs? Okay, I think okay, by giving IDs as example. So I think this is the good example, right? This is exactly what we are doing. Sorry, this is what is exactly what we are doing in this example. So S of 0, thread 0 will access S of 0, thread 1 will access S of 1, and so on. So this access pattern is exactly similar to this. S of 0 is accessed, S of 1 is accessed, S of 2 is accessed, and so on. Thread 31 will access S of 31. And since all these are in the different banks, this all words which are consecutive are in the different banks, they'll be accessed in parallel fashion from the shared memory, and hence there is no bank conflict. Since all the work threads are accessing the words which are in different banks, there is no bank conflict. And yeah, I hope that is clear, but if still there is any confusion, Gokul, then you can unmute yourself and ask. Okay, I am assuming that there are no questions further. Okay, anyway, so if there are no questions further, let us continue. I have one more question for you, which is to write the code corresponding to the case when there will be bank conflict. So that is the next question. Please write the code corresponding to the case when there are, I mean, when we have the bank conflicts. Bank conflicts, that is the second case. So please take some time to write out that code, and please post your answers into the chat, or at least some expressions like this, like what we'll do for that case, like we did here, right? So please write the code corresponding to that and post them on the chat. I hope that question is clear. Okay. To avoid bank conflicts, so to avoid bank conflicts, necessary steps have to be carried out only inside kernel, right? Nothing has to be done inside the main function. Yes, that is correct, Harish. Whatever we need to do, whatever steps that we need to take for removing the bank conflict should be done from within the kernel, because the shared memory is itself declared inside the kernel, right? So uh, yeah, that is the answer. Yes, the answer is yes. Rishikesh is suggesting S of 3 equals to thread ID x dot x. Hmm. Okay. Varun is saying ARR of 0 equals to thread ID x dot x, but I don't know what will get assigned to ARR of 0. That is fine. But okay, let us take first of all this Rishikesh and Varun's suggestion. So what both of them are trying to do is they are trying to take some ARR of random index, which is between random index between 0 to 31, and they are doing some thread ID x dot x, right? So my question is, will this work out? I mean, okay, let us understand why will this not work out. The answer lies within these 4 points only. If you try to do something like this, s of some id equals to thread id x dot x, is this the case for no? Is this the case for complete bank conflict or some bank conflict? The answer is no. Let us understand why the answer is no. If you see this exception part, I think you people didn't catch up this exception part properly. Here, if you see, each thread uh, each thread is accessing, assuming that this thing is written inside the kernel, each thread is accessing some location. Let us say that location was ARR of 10, right? So each thread is accessing the ARR of 10. And what is this ARR of 10? Let us understand. This ARR of 10 is being accessed by the warp threads. So warp threads are accessing same word, right? Because each thread will be accessing the ARR of 10 only. So warp threads are accessing same word from the same bank. So warp threads are accessing same word from the same bank. If that is the case, then this is the case when we fall in this exceptional part, and in that case the accesses won't be sequential. So if you are following it properly, then actually this is the special case. Whatever this Varun and Rishikesh has suggested, this is the special case where there won't be any bank conflict actually. I hope you are getting it. So this both suggestions are for no bank conflict actually. Okay, coming to the Gokul suggestion, ARR of thread ID x dot x mod 512 equals to x. I'm assuming that x is some random constant or some variable, Gokul, but let us think about thread ID x dot x mod 512. I think still this will be coalesced, right? Because let us say from thread 0 to 31, 0 to 31 mode 512 is again 0 to 31. And if you are doing that, then again it is the example of fully no bank conflict, not no bank conflict. So this again is the example of no bank conflict. So cool. I hope that you are getting this. So this is the example of no bank conflict. Let us come to Harish's suggestion. As of thread id x dot x equals to thread id y dot y. So I am not able to understand this suggestion, that how can this lead to no bank conflict? Sorry, how this can lead to complete bank conflict? So this is the example of no bank conflict. All these three are the example of no bank conflict. First three. Then I think this is also the example of no bank conflict only. But I'm not able to catch up this thread ID y dot y. Assuming that we have just one-dimensional thread block. Let us assume, let us for the case of simplicity assume that we have only one-dimensional thread block, and in that case we won't have thread ID y dot y. So just don't try to mess up with the dimensions. Let us keep the dimensions as just one for the thread block. Considering, keeping that in mind, what can be the answer? Okay, so moving on, Rishikesh is again suggesting that thread ID x dot x into 32 is equal to thread ID. I think this one is correct. Let us see this. I'll come to this thing. Can you explain why it's not a bank conflict again? Okay, Jayaraman, can you unmute and tell me which one is not a bank conflict?
Yeah.
Yeah. Your voice is breaking. Can you speak up louder, or can you speak again?
Yeah, I was meant. Uh, I was not sure what.
Sorry, I can't. I'm unable to uh, catch you fully because of some noise issue. If someone else is able to hear him, and if if anyone else is able to understand his question, then please unmute yourself and tell me what he's. Okay, Varun's example. Okay, this. I think it's this. Okay, so again, let us understand this. What is ARR of 0 equals to thread ID x dot x doing? So first thing that you should observe is that we are accessing the same memory location, right? The array ARR is shared array. The way we have done here, it's a shared array. And what we are doing, we are accessing the same memory location, if you see, yeah, which is ARR of 0. And as we saw, if we access the same memory location or the same word, because it's an integer, it's one word. So if walk threads, so okay, let me come back. So here what each and every thread is doing, each and every thread is storing thread its ID, which is thread ID x dot x, into the same word, which is ARR of 0. So in other words, what is happening is each walk thread, so walk threads are accessing same words from the same bank. And if that is the case, if the walk threads are accessing same words from the same bank, then their requests are not serialized or sequentialized. And if their requests are not sequentialized, then it is the case of no bank conflict. Bank conflict only occurs in the case when we have sequential accesses. So accesses to the same banks are sequential. In that case only we'll have bank conflict. If accesses are not sequential, as it is the case in this exception, then there is no bank conflict actually. So I hope you are getting it. So if there is any further question, then please feel free to ask. We'll come to this, Gokul. Does bank conflict occur only when whole warp doesn't access the same bank? Probably we'll see a couple of slides related to this. So I'll come to your question later. Yeah, but let us move on. So yeah, I think that was a good discussion. So let us see the code corresponding to the bank conflict. So this is the code corresponding to the bank conflict. So we have this kernel bank conflict, and inside this we are declaring some shared array. Sorry, we are declaring some array of size 1024 which is shared, which means that it is common for the threads across threads of the thread block. And the access pattern that we are trying to do now is this: as of 32 into thread id x.x equals to thread id x.x. So let us understand what will happen and why it is the case for the why this code causes bank conflict. So let us understand what will happen. So thread with id, let us take warp threads first. Yeah, so let us take warp threads. Thread with id 0 will access the memory location as of 0. So thread with id 0 will access as of 0. Thread with id 1 will access as of 32. Thread with id 2 will access 64 as of 64. Thread with id 3 will access 96 and so on. So if you see this words, if you see this pattern 0, 32, 64, 96 and so on, where all these words are stored. If you observe carefully, where all these words will be stored. Let us come back to our this example that I posted in chat. If you see, ARR of 0 or S of 0 is stored in bank 0. If you follow this pattern, then if you will again observe that 32 will be accessed in stored in bank 0, 64 will again be stored in bank 0, 96 will again be stored in bank 0. If you continue populating like this in the way I have done here, so all these words here given here 0, 32, 64, 96, all this will be stored in bank 0. All these words will be stored in bank 0, and if that is the case, if let us come back to our slides. So if that is the case, all these words are stored in the same bank. And now if you see carefully, okay, there is some noise from someone's end. I request every one of you to mute. Is there someone who is unmuted? Let me quickly check. I think this is okay. In case you have any questions, then please unmute yourself and ask. Otherwise, please mute yourself so that we can have minimal distractions during the classes. Okay. Anyways, let us come back to our discussion. So we saw that this word 0, 32, 64, 96 all are stored in the same bank, which is bank 0. And if you see this, the definition of bank conflict. If the warp threads are accessing same bank and different words within the same bank, then accesses will be sequential. So that is exactly the case here, right? The warp threads, which is 0, 1, 2, threads with ID 0, 1, 2, and so on, they are accessing word 0, 32, 64, 96, which are within the same bank, and these are not the same word, which was the case in which Varun and Rishikesh suggested the same word. These are not the same word, and these are also not these are from the same bank, and these are also not the same word. So this is the example for the bank conflict. So this is typically the example for the bank conflict. I hope you're getting it. In case there are any questions further, then I'll quickly move to the chat. In this case, many unique warp threads access the same bank. Is that CRT, sir? In this case, many unique warp threads access the same. Yeah, if in this case there are many threads accessing the same bank, and this is precisely the reason for the bank conflict. But I would like to add one thing here. They are accessing the same bank, but the different words within the same bank, and that is why this is the bank conflict. If it would have been the case that they are accessing the same word from the same bank, then there won't be any bank conflict. So again, different words within the same bank will cause bank conflict. Same word from the same bank will not cause the bank conflict. I hope that is clear. there are any questions, then please feel free to unmute yourself and ask. Uh, yeah, I'll just wait here for a few more seconds and then we'll move on. Okay, there is some question, are there always only 32 banks? Yeah, for I think for current technology, it's the shared memory of the GPU is having only 32 banks. But in future, it might change. So I can't comment about. Yeah, I mean currently it's 32, but in future it might change. That's the answer. Okay. I think I'm assuming that there are no questions. Then let us continue with our slides. Okay. So we have these three cases here. So let us understand what is happening. So this 1, 2, 3, and so on are the IDs of the thread till 31. Warp threads are these are the IDs of the warp threads from 0 to 31. And this yellow boxes, three-dimensional yellow boxes, represents one bank. So this is bank 0, bank 1, bank 2, and so on. And inside them, if you see this orange or red boxes, represents the word, a particular word inside that bank. And if you see here, each thread is accessing some word from different bank. If you see, each word thread is accessing some word from different banks. So I would like to ask you people, which scenario is this? Is this the scenario for no bank conflict, or is this the scenario for the bank conflict? Please post your answers in the chat. I mean, this would be very quick if you have understood the previous slide completely. What this first thing, this first one represents? Is this the complete bank conflict? Is this the bank conflict case or no bank conflict case? Yeah, I think you people have understood it. No bank conflict. So yeah, no bank conflict. So this case is the one for no band conflict. So first one, I think it's pretty much clear after understanding the previous slide that this is the case for no band conflict. Now let us come to the second case. Again, we have this threads, warp threads having ID from 0 to 31 and banks which are represented by this cuboid or yellow cube. And each this orange box are the words within that bank. And here if you see, the threads are accessing the banks in some order, and I would like you people to think about which scenario is this. Is this a scenario for bank conflict or no bank conflict? Please think about it and post your answers in the chat. Please think about the second case. Okay, Shikesh is saying no bank conflict, no bank conflict. Sorry, bank conflict. Shikesh is saying bank conflict, conflict, no bank conflict. Okay. Varun is saying no bank conflict because thread 16. Vikas is saying no bank conflict. Okay, so those of you who have said no bank conflict, would you like to add any supporting argument for your answers? Why you people are saying that there is no bank conflict? I'll quickly go back to the slide. Can you explain why there is no bank conflict, or I mean, what was the reason that was in your mind when you told that there is no bank conflict?
Sir, bank conflict I can explain. Like bank 0, two of them are like 0 and 16 are accessing to different locations in bank 0.
Okay.
So it is bank conflict.
Yeah, so it is bank conflict, but I think Someone? You wrote that no bank conflict.
No,
Right?
sir, like Rishikesh.
Okay, you are sorry. Yeah, I think that is the precise explanation for it. So let us understand. So as Rishikesh was saying that since two threads here, if you see thread 0 and thread 16 are accessing the word from the same bank, and if you see this is not this, I mean they are not accessing the same word, they are different words. So they are accessing different words from the same bank. So here their requests will be sequentialized, and if you see here, if you consider all the bank, then the maximum amount of sequentiality involved, or the maximum amount of sequential request that a bank has to, I mean maximum amount of memory request that bank has to serve sequentially is 2, right? If you see any of the bank, then the maximum amount of request that has to be served sequentially by any bank is 2. There won't be any request that should be that have to be served sequentially having size more than 2. So in other words, this is also known as two-way bank conflict. So I hope that you are getting it. So this is the example of two-way bank conflict, and yeah, this is the case for the bank conflict first of all, and it's a two-way bank conflict. I hope that is clear. If there are any questions, then different threads accessing different words from the same bank results in sequential operation. Yes, that is the correct reason why it is the bank conflict. Here, different threads, which is thread 0 and 16, are accessing the different words from the same bank. So it is leading to sequential accesses and hence the bank conflict. So I hope that it is clear. Yeah. Okay. So I'm assuming that it's clear to everyone. So okay. So let us move on further. So what is, I mean, again, what is this third scenario saying? Is it bank conflict or is it no bank conflict? Please put your answers in the chat. I think it will be much easier now after understanding first two and that previous slide. Is this the case for bank conflict or no bank conflict? No bank conflict. Okay, I guess. Okay, I guess you people are getting it correctly now. So yeah, again, this case is for no bank conflict because as you see here, each thread, although their access pattern is arbitrary, I mean they are accessing in some jumbled manner, right? Thread 1 is accessing some third bank and so on, like access pattern is jumbled. But the important point here to observe is that each thread is accessing some word from the bank and no other thread is accessing from the same bank. So all the threads are accessing from some bank which is I mean which is unique to that thread. So it won't happen. It is not happening here that thread 2 is accessing from some bank and also some another thread is accessing from that same bank. So if that is the scenario here, then again this is the example for no bank conflict. I hope that you are getting it. Just let me quickly go to the chat to see if okay, I think yeah, everyone is getting this point. So let us move on further. Okay, so let us understand these three cases again. So I guess first scenario, I guess everyone will be understanding it. Now this first one is again for the no bank conflict. So I'm just skipping this because I'm assuming now that based on our previous three example, you will be able to understand why this is no bank conflict, right? Because even though the access pattern are jumbled up here, but still each thread is accessing some word from the bank and no other thread is accessing the same bank here again, like the previous example. So again, this is the example for no bank conflict. But what about these two example, this second and third one? Are they the example for no bank conflict or they are the example for the bank conflict? Can you people quickly type in the chat what do you think about these two cases? I'll pause here for some time so that you people can think about this. Let me Rasita is saying no bank conflict. Vikas is saying no bank conflict. Is there any bank? Is there any possibility of locality in bank conflict access? Locality in bank conflict access. Gokul, I didn't catch up your question. Would you like to elaborate on this? Locality in bank conflict access. Rishikesh is saying no bank conflict for both. Okay. No bank conflict, no bank conflict. Jayaraman is saying no bank conflict. Vasanta is also saying no bank conflict. Okay. I think uh, I think you people are getting correctly here. So these two are okay. Let us understand these two cases. So these two cases are typically the case for that the exceptional one, right? That we saw. If you remember here, this exceptional case, that if walk threads accesses the same word from the same bank, then they are not sequentialized, and hence there is no bank conflict. So if you see here, for these two cases, there are walk threads. For example, 2, 4, 6, 7, and 9. These threads are accessing the same word from the same bank, and if that is the case, we are calling it that exceptional case part. So the accesses won't be sequentialized to the bank pi, and this as they are accessing the same word, the request would be served parallelly for 3, 4, 6, 7, and 9. So this is the case for no bank conflict. Similarly, this one, since the this all 0 to 16 threads are accessing the same word from the bank 12, the request won't be sequentialized, and all these threads will be served in parallel, and hence again there is no bank conflict. Okay, similarly for this bank 20. So I hope you are getting it. So this case, again, this both case are for the no bank conflict. I hope that is clear. If there are any questions further here, then we can take those up. Else we'll move on. Okay, I search since the words are sequential. Would loading next word be fast enough to not worry about due to locality. Okay, I think there are some since this shared memory is again the part of L1 cache, I think locality will come into play. I mean, the adjacent word, as we saw in that spatial locality, right? That if adjacent words are being accessed, then due to spatial locality, we'll get some performance benefit. So I think that thing also comes into play. But what's more important here is this bank conflict and the way, I mean, the way we are arranging the words in the different banks. So your consecutive words are arranged in different banks, and this will give us the performance benefits here in case of GPU. And I think that locality aspects will also come here, but I don't think that it will have much effect on the performance compared to this parallel access across the bank. So yeah, that is what I can say. I'm not much sure about this thing, but yeah, I need to check. Since the words are sequential, would loading the next word be fast enough to not worry about due to locality? I'm not 100% sure about it, but yeah, I mean, locality will come into picture here. Okay, I think there are no further questions apart from this. Yeah, I think there are no questions. Then let's move forward. Okay, so let us briefly touch upon the texture memory now. So as I told in the first lecture of the our memory, first of the memory lecture, that this we have this texture memory, and it's across all the threads of across all the threads of the grid, and I mean common across all the threads of the GPU. So and it's also read-only memory. So so I mean it's read-only memory, so it can be used for storing some metadata, like yeah, if you want to store some data structure for keeping track of data which is present inside the global memory, then you can do it using texture memory. But more typically, if you remember that this Texture memory is optimized for the 2D special accesses. So let's say you are accessing some memory location ij, then access to the I plus 1j, I minus 1j, ij plus 1, ij minus 1, and so on, which are within the close, the cell which are within the close, uh, spatially close to that cell ij, will be, can be accessed quickly if you have placed your that 2D array or matrix into this texture memory. So that is one point. It is optimized for the spatial accesses or the, uh, I mean, geometry, some kind of geometrical accesses. And its second thing is it's only read-only memory, so it can be used for storing metadata. So let us see how to access this texture memory. So first of all, in order to access the texture memory, we need to declare a variable of type texture. So this name of this variable is text, and yeah, this is some sort of data type texture, and we need to specify that this variable text will be pointing to some array or some two-dimensional matrix which is storing the float values. The second parameter says that it's a two-dimensional matrix or two-dimensional array, and then we are specifying that it's CUDA read mode element type, meaning that we are only allowed to do read operations, which is actually correct because this is only read-only memory. So that is how you declare this variable of type text, and think of it like some pointer to the array. And then once we have declared pointer to the array, we need to point it to the actual array, right? So for doing that, we use this CUDA bind texture to array function, in which we pass this text as the argument, and CUDA array, which is the array which is allocated on GPU using CUDA malloc and initialized using CUDA memory. So that array will be binded with this tech pointer or some sort of pointer, which is actually it's a variable, but let us assume it, let us consider it as a pointer. So this both will be bind, and now tech will be having this CUDA array, and it will be there. Okay, so this thing will transfer this CUDA array into the texture memory. So memory allocation will be done, and then the CUDA array will be transferred to the texture memory, and that memory can be accessed using this tech variable which is declared here. So again, this is some sort of declaration of tech variable. Here, using this statement, we are allocating the memory as well as initializing it. Yeah, so I hope that these 2 points are clear. So once allocation and initialization is done inside the texture memory, what we need to do is to access that memory, obviously. So that can be done inside the kernel using something called as tech2d function, and it can be done using tech2d function, and we need to pass this variable tech, which actually will give us the hold to that array that we want, array or matrix that we want to access, and then we need to specify the dimensions like ij we used to do for 2D matrices, right, on C program or CUDA program. So that we need to pass 2 arguments as well as the tech, which is the name which is the some sort of name for that array that we have allocated in the texture memory and initialized it. So I hope that this is clear. If there are any questions on this slide, then please feel free to post them on chat. So what is the element type for? Okay, I didn't catch up on this question. Where is the element type? Are you talking about this data type? It is for the it shows that what kind of data that you are storing in inside this tech matrix or something that we have allocated in the texture memory and initialized it. It says what type of data you are storing inside it. I hope that was your question. If not, then okay. The CUDA read mode element type. Okay, so this part says that we are only interested in reading this. we will be only reading this. I mean, will be only reading this memory which will be allocated on the textual memory, and in fact that is true, right? That it's only read-only memory. So it suggests that we'll be accessing this matrix stack which is allocated on the textual memory in read mode, is what it is suggesting. It is what the meaning of this thing. I hope that is clear. CUDA read mode element type. If there are any further questions, then you can ask. Go ahead. Okay, Ishwan is saying, where is the texture memory located? Is it visible only within a block? Okay, so texture memory is common across all the blocks, all the grids. So it is something. It's located at the same place in the hierarchy as the global memory. So it is common across everything, all the threads of the GPU, not just the warp threads or the block threads. I hope that is clear. Across all the threads, all the grids, everything is common, like the global memory. Okay, I am assuming that there are no further questions. Okay, let's move on then. So let us try to understand this one example. So let us assume that we have allocated the we have declared this variable of type tag and binded it with some array. Here, let us say we have globally declared that tag variable and then binded it with some array which was declared on the GPU here in the main, and then we are launching the kernel. And then while launching the kernel, we have this 4 arguments, right? One is output. It's a pointer of type float, and its name is output, which can point to some float array, and it will be actually stored for. It will be useful for storing the output, since we can't write into the textual memory, right? So since we can't write into the textual memory, we'll need to store after performing operation, we need to store output in some array, and that is what is this output array, which is of type float. Then we have this width and height of the image that we are going to transform. So it's some sort of an image transformation function, and width and height is the height and width of that image. Then we have this theta, which is of type float, and which is some which actually denotes some degree by which we want to tilt or flip that image. So I hope these arguments are clear. Then we are calculating x and y, value of x and y, which are unsigned integers, using this standard equations that we have. And then we are doing some operation using this 4 line. So what these 4 lines are doing is they are taking these values of x and y, and based on these values of x and y, they are calculating x and y as well as width and height, and theta, they are calculating the value of tu and tv. So based on this value of x, y, height, width and theta, they are calculating the value of tu and tv. So actually, if you see, this x and y are the original location of some particular pixel, and this tu and tv are the modified location or the new location of that particular pixel. So we want to we want to shift that pixel which was at location x, y to tu and tv. And in order to do that, what we do is we access the texture memory using tag2d. We pass this argument tag, which points to or which holds the pointer to that matrix which is allocated on the texture memory, and then we pass this tu and tv. So this will give us that element, and then we'll store that element into the xy memory location. So please note that this is the access of the 2D matrix in 1D form, y into width plus x. So at y into width plus x, which is yx memory location, we are storing this element which is present at tu and tv. So actually, if you see what will be the output of this program, if you take some input image like this, then this input image after execution of this program will be tilted. So based on this theta function, theta parameter which we pass, which determines the tilt that we want, which determines the tilt that we want for this image. Based on this theta parameter, the image will be tilted accordingly, if you see. So yeah, this is the input and the output for this program. Any questions up till this point? Okay, I'm assuming that there are no questions. And if that is the case, then let's move on with our next slide. Okay, so next thing is the constant memory. So we have seen texture memory and it's one example. So let us also see the constant memory and one of its example. So again, this constant memory is again the read-only memory. So we won't be able to write, write anything as such. So it's only for storing some metadata, again, like the data structure using which we will be, uh, which can be used to manage other data which is present in global memory or something like that. So it's again read-only memory. So it can be used for storing metadata, and its size is 64 KB per SM, which is streaming multiprocessor. And okay, and then let us understand this thing. So let us say that we want to define we want to define some variable or an array using variable and array inside this constant memory. Uh, yeah, so okay, let us say that we want to define some array inside this array or variable inside this constant memory. Then how can we do it? The way we can do it is very similar to the way we do it for the shared memory. So for shared memory, what we do, if you people remember that for shared memory, we do this underscore underscore shared underscore underscore, then the data type, and then the identifier for that array, and then the name of that array, right? So we used to do that. It's very similar to this here. Instead of that shared, we use this keyword constant underscore underscore constant underscore underscore, and then the data type and the identifier, and then the size of the array that we want to declare in the constant memory. So this is one thing. This is the definition for it, the way we'll declare it. Then second thing is how can we access it or initialize it from the main. So here one point you should note, we can only initialize it from the main or the CPU. Since it's a read-only memory, if you people note this thing, since it's only a read-only memory, we won't be able to access, we won't be able to write into it from the GPU. So if we want to initialize it, we only can, we can only initialize it from the CPU. And to initialize it from CPU, there is a function. This function is CUDA memcopy to symbol, and this function will initialize this array meta using some h meta, which is the variable on the CPU. And if you see, this syntax is very much similar to CUDA memcopy, right? And in fact, the function name is also CUDA memcopy to symbol, like we used to have that CUDA memcopy from device to host and those functions, right? So here it has three arguments. One is the constant memory, or the uh, pointer to the constant memory. Second parameter is the pointer to the CPU array, or CPU array, or the pointer to some CPU memory location. And the third argument is the size of the data that we want to transfer. Here, since we have just one array of just one size, we want to just copy one element of size unsigned, because this is of size unsigned. So I hope that is clear. One is declaration or definition. Then second is its initialization, which is from CPU. And again, after doing all this declaration and initialization, we need to access it. So how can we access it? It's simple. We need to do this thread id x.x equals to meta of 0. So assuming that this data is some array allocated on GPU and thread id x is the ID of the thread, we are initializing each element in this array based on the ID of the thread to the value which is there in this meta of 0. And please remember that we are just doing reading operation. We want to be able to write in this meta. So I hope that is clear. There are some questions. Okay, okay, this is done. Sir, does the calculation happens in Yeah, you can do the calculations in the texture memory also. So that won't be the issue. But the thing is that it is optimized for, I mean, if you want to use it, if you want to use the texture memory, then use it for the geometry based operation where you are accessing some memory location and all its adjacent memory location. Like if you are accessing some matrix, then and it's some entry like ARR of ij, and if you are also if you are doing some geometry operation, then you will also be need, I mean, in a need of accessing its adjacent uh, memory locations like ARR of ij plus 1, ij minus 1, I minus 1 j, I plus j, and all those things. Okay, okay, you are telling that, okay, it's correct that it's a read only memory, but you can read its value and do some calculations based on it. So I took it in that way. I didn't, I mean, I don't okay, I'll put it like this. I was not trying to say that you are trying to write inside the texture memory, but based on the value that is inside the texture memory, you can do some calculation and write the output in some array which is allocated on GPU. So let me clarify my point here that I was trying to say. So here, if you see, we are just reading the texture memory. The output that we are writing is inside some another array which is allocated on GPU, which is output. So please assume that this output is a pointer pointing to some array which is declared on the GPU using allocated on GPU using CUDA malloc, and we are writing inside this output array. So writing can't be done obviously on the textual memory since it's a read-only memory, but you can read its value and do some calculations based on it and place its value in some output array which is not the texture, I mean, which is not inside the texture memory. So I hope that is clear, Gokul. Okay, so but how are we allowed to load our data into that memory? Okay, let us come to that. So if you remember this, we are doing this thing CUDA bind texture to array from the CPU. So you are not allowed to load the data into it since it's a read-only memory, but from GPU. Obviously, you can load the data from CPU. Otherwise, there won't be any use for it, right? If you are, I mean, if you have a memory into which you can load anything, then there is no point of using it. So you will be able to load it, but from CPU. And from GPU, you will be only access. You can only access it for reading operation. In the same way, we have it for constant memory, right? That we can load it from the CPU, load the value into it from CPU, and access it inside the GPU for read-only operation. So I hope that is clear, Gokul. Okay, okay, I think it's clear now. Okay, so let us move further. So this is the typical example related to the constant memory. So I mean, this is a very simple example and it demonstrates the same thing that we have done here. But let us see it once quickly. So we have this constant memory declared here using constant underscore underscore constant underscore underscore keyword. Then we have yeah, we have declared it in the same way as we did here. If you see here, then okay, yeah, then let's come to the main first. So we are declaring this h meta, which is some variable on CPU, which is initialized to 10. Then what we are doing is we are doing CUDA memcopy symbol the way we did here, if you remember. And we are copying the value of h meta to meta. Meta is a constant variable declared on the GPU's constant memory, please remember. So from CPU variable, we are copying the data to GPU's constant memory, and the size of the data transferred is one unsigned integer. Then we are declaring the pointer to the unsigned integer, which and the name of it is data. Then we are allocating it, uh, allocating the memory on GPU using CUDA malloc. And this is, please remember, this CUDA malloc allocates the memory on GPU's global memory, not constant memory. So this is data is now pointing to some array of size 32 in the global memory. Then this data is passed to the GPU kernel, T kernel, and it is launched with 32 threads. And what this T kernel does is it takes this data, which is address pointing to some array on GPU of size 32. It does data of thread ID x dot x equals to meta of 0. So meta of 0 is 10, if you remember. We have copied it from h meta to meta. So each thread from 0 to 31 will initialize that array of 32 size to the value 10. So each and every element from 0 to 31 will have value 10 inside this data array after this kernel launch. And after that we have this CUDA device synchronize, and then we are printing the data. And again then we have CUDA device synchronize, and then we return. So I hope this is clear. So this program will print 1032 number of times. Any confusions till this point on constant memory or any aspect related to it? Okay, I'm assuming that there are no questions. In that case, let us move further. Okay, so let us move further with this compute capability. So if you people know, then if you people know, then there is some version number associated with each GPU. So you might have heard that let us say that NVIDIA RTX 20 or NVIDIA RTX 3050 has compute capability of 86 or version number as 86. So what is this 86? So this 86 is divided into two parts. One is the major number and minor number. So that out of that 86, 8 is the major number and 9 is the minor number. So let us say that if the version of your GPU is 66.2, then 6 is the major number and 2 is the minor number. And what these things, first of all, we understood that this is major number, minor number, whatever it is. But what this thing denotes to us. So like GPU is an hardware, and hardware is provide some version number based on the features that it is supporting. So let us say that you have some old GPU which was having version number let's say 5.0. Then it might support some feature, but let us say you bought some new GPU which has some higher version number, let's say 6.2 here, that which is mentioned. Then it might support some additional feature that old GPU 5.0 was not supporting. So this version number, which is composed of two things, major and minor number, denotes the features that are supported by GPU hardware. And yeah, again, this version numbers are given for the GPU hardware actually. And typically, what is the use of it? So you can use this version numbers. While the compilation of program, you can specify this version number using this flag arch equals to sm underscore then that version number, which is composed of major and minor number. So you can specify this during compilation. So its typical use is this. So let us say that you have some CUDA compiler and you are compiling the code using you are compiling your CUDA code using that CUDA compiler. So by default it will compile it using some default version number, let's say 62. But let's say that version 62 was not having few of the features that you were using in your code. Let us say that feature, let's say your compiler, NVC compiler was by default compiling your code with version number 62. But let us say that you have used some functionality like atomics on double precision floating point numbers, which was not supported by this version number 62. In that case, you need to explicitly mention to this CUDA compiler that please compile my code using some higher version number by specifying this flag arch equals to sm underscore, let's say 75, which has that support for atomics on double precision floating point numbers. So it might, you might sometimes need to use this thing, this arch flag, and provide this at runtime so that your application can be compiled accordingly. Otherwise, compiler will throw error, compilation error. So I hope that is clear. And second thing is the CUDA version. So CUDA version is related to the software. So CUDA itself is a software which manages the, in some sense it's related to the, it's somewhere related to the hardware, but it's a software written for the hardware. Think of it like that. So CUDA version is a software version. So whenever you say that I have CUDA 10.1, it's the version of the CUDA. But this major number, minor number, which is given for the GPU hardware. So this compute capability is for the GPU, which gives the version for the GPU hardware, while the CUDA is a software concept, and the CUDA version gives it's something related to the software version, and CUDA version is somewhat related to the software. I'll this compute capability is for the GPU hardware. I hope that this distinction is clear. If there are any questions here, then quickly. Okay, I guess there are no questions. So, okay, so key takeaways like CUDA is something related to the software, and compute capability is something related to the GPU hardware, and it has some version number, which is divided into two parts: major number and minor number. And sometimes you need to specify this thing while compilation, and that thing you can do it like this: nvcc minus arch equals to sm underscore, let's say 75, and then you will specify that hello.c. Something like this should be done if you are using some very um, high-end features that are not supported in the lower versions. So yeah, that's the brief takeaway. Okay, anyways, let's move further. So let us see this. So there is this major number corresponding to the family of GPUs. So for Tesla family of GPUs, the major number was 1. So this Tesla family of GPUs were supporting some features, and based on it, it was given major number. It was given major number 1. Then came the Fermi architecture, Fermi family of GPUs, uh, which supported few additional features apart from those which were supported by Tesla. So they were given version number major number 2. So 2.0, 2.1, and so on will be there, and so on. So if you see this Ampere family, family of GPUs, Ampere family of GPUs are given version number 9. So if you see this Ampere is it will support all the features that are supported by all its predecessors. And yeah, so please note that Ampere will support all the features which are supported by all its predecessors, because it has higher major number. And yeah, so it is, it's the latest one, latest family of GPUs. And yeah, so based on the major number, it might support additional features. So higher the major number, more additional features it might support. And there is one point missing here. If you say there is no 4, there is no 4 number. From 3 it's directly 5. Does anyone know what is the family of GPUs associated with that major number 4? uh, can I mean can anyone quickly type in the chat? Okay, I think there are no answers. Anyways, okay, so the answer to is it is like quite bit funny. Like there is no family of GPUs associated with that major number 4, and that is because NVIDIA planned to skip that major number 4. So that is one thing. Apart from that, there are also two more major numbers, 10 and 11, which are corresponding to Lovelace and Hopper family of GPUs, which are still under the prototyping phase. So if you see this, Lovelace and Hopper family of GPUs are still not out. You will see up to this Ampere. So Ampere family of GPUs are out, but these two are not out, and still it's under the construction phase or the prototyping phase. So yeah. So these are the major numbers and the family of GPUs corresponding to it. And I hope that it's clear. Like the version number denotes the uh, some additional features that a particular family of GPU provides compared to its predecessor. Okay, so let us quickly look into this. So this these are the major numbers, or these are the version numbers in another way. In some sense. So this 2.x is a version number, then 3.0 is some version number, then so on. Like 8.0, 7.x, 6.x, and so on. So if you see this 2.x provides these three functionalities, these three more functionalities than its predecessor, which was 1.x. So as compared to 1.x, 2.x supports these features: atomics with ints and floats, warp voting. There is something called as warp voting, which we'll learn if we get time. Then sync threads. Yeah, so these three features are supported by the 2.x family of GPUs, which are not supported by 1.x. So if you see here, Tesla won't support these things. Tesla won't support these three things. Sorry, Tesla won't support these three things, but Fermi family of GPUs will support these three things. And if you see 3.0, then 3.0 supports unified memory, which is some sort of common memory between CPU and GPU. I mean, not common memory, but the memory that is maintained both in the CPU and GPU, and it is kept consistent across CPU and GPU. So that unified memory is supported in 3.0, which is Kepler family, which is not supported in 2.x, which is Fermi family of GPUs, and so on. So if you see, as we move ahead, there are more and more features that are getting supported. So from 3.5 onwards, we can see that dynamic parallelism is supported, which means that we can launch the kernel from another kernel. So that is what is dynamic parallelism, which is supported from 3.5 onwards. Then there is atomics with double, which is being supported from 6.x onwards, 6.0 onwards. Then from 7.x onwards, you will see that tensor core is supported. Then from 8.x onwards, at 8.0 onwards, you see that hardware async copy is provided. So you can copy data between CPU and CPU asynchronously. So I hope this is clear. So as we go more, more farther from 1 to, let's say, 10 or 11 here, 1 to 10 or 11, you can see that more and more features are getting supported by the GPU, and that is what is compute capability. It decides the capacity. It shows the capability of hardware to support some or multiple features as compared to its predecessor. I hope that is clear. Are the RTX 3000 series part of the Copper series? No. RTX 30 is not part of the Copper series, I guess. As far as I know, it is not part of the Copper series. But I'm not sure to which series this RTX family belong. I need to check. This RTX series is not part of the Hopper series. Is probably, I'm mostly sure about this, but you can check this thing on Internet or the NVIDIA's documentation. Yeah, so let us move on further with this, and let us conclude today's lecture with this last slide. So we studied about this CUDA, which is the abbreviation for Compute Unified Device Architecture, which is hardware as well as the software architecture. And it allows enable GPUs to execute programs written in C, C++, Fortran, and OpenCL and other languages. Even PyCUDA is there, so you can also use Python. So a CUDA program has typically one kernel launch, which launches some GPU function with some threads, and that kernel is executed in parallel by multiple threads. So yeah, so a kernel executes in parallel across a set of parallel threads, and programmer can organize these threads into thread blocks and grids. We saw that how we can specify the configuration for grid and thread block while launching the kernel. We saw this part, the computation aspect. Then we saw that GPU instantiates a kernel program on a grid of parallel blocks. So we also saw that that's right. Whenever we launch a kernel, it is associated with some grid. If you remember, in the computation lecture, we saw that this thing. Then each thread within a thread block executes an instance of kernel and has a thread ID within its thread block. Program counter register per thread private memory input and output results. So each thread within the thread block will have all these things. Thread ID will be there. You people know, right? We can access it using thread ID x.x. Then there will be also program counter, since each thread is executing different instruction, which might be different than what other thread is executing. It needs program counter to keep track of what instruction to execute next. Then it also has register. Per thread registers are there. Then per thread private memory, which is not some special memory. It's the global memory itself, and it's some part of the global memory. And input and output results are there. Then A thread is set of concurrently executing threads that can cooperate among themselves through a thread block is a set of concurrently executing threads that can cooperate among themselves through barrier synchronization and shared memory. So we saw this, right? That within the, for the threads within the thread block, we have some fast synchronization, which is sync thread, which is the barrier synchronization that we saw in yesterday's lecture, right? That sync thread, and shared memory also we saw in last to last lecture. Then a grid is an array of thread block that executes the same kernel. And yeah, so we saw that when we launch a kernel, it is associated with grid. And this grid, every thread in this grid executes the same kernel and reads input from global memory and writes result to the global memory. So we know this, right? This thing we are clear. So each thread has a per thread private memory space used for registers, fills, and function calls and C array variables. So this private memory space is nothing but the some part of global memory that is provided to each and every GPU thread during the kernel launch. So if the registers, if the data can't be stored in registers which are allocated to that particular thread, the data will spill into the global memory, and that is what is some private memory space which is provided to each thread. And also for function calls, we'll have function call stack for each thread on the GPU. And C array variables, yeah, we know this, that we allocate using CUDA malloc, and the C arrays will be stored, GPU arrays will be stored in that global memory, which is something, which is nothing but this private memory space. And yeah, last point is thread block has a per thread, each thread block has a per thread shared memory space used for inter-thread communication, data sharing, and result sharing in parallel algorithms. So we also know this, right, that each thread block has the shared memory space or the scratchpad memory that we learned, and it is used for inter-thread communication. So a thread within the thread block can write to that shared memory space, and other thread can read from it. So inter-thread communication is possible among the threads within the thread block. Data sharing can also happen in the similar manner, and result sharing is also possible. A thread can write some result into that shared variable, and another thread can read it. So yeah, these three things are possible for the threads of the thread block using shared memory, and it can be used in parallel algorithms. So I hope there are no questions. There are no questions up to this point. I think this slide must be clear because we have already seen all these things in past lectures. But this is just for briefing up or summing up all the things that we saw till now. So, but just in case there are any questions on this slide, you can unmute yourself or can type in the chat.